Imagine, for a moment, the fastest, most powerful computer in the world in 2019, a behemoth named IBM Summit, capable of performing quadrillions of calculations per second. Now, imagine a challenge so complex, so intricate, that even this titan of technology would grind away for over 10,000 years trying to solve it. Sounds daunting, right? Well, in 2019, a team at Google tackled such a problem. And they didn't take 10,000 years. They didn't take 1 year or even 1 month. They solved it in just over 3 minutes. Mind-blowing speed. A technological leap that seems almost unbelievable. But here's the kicker, the twist that makes this story so intriguing. The problem itself? It was, by all accounts, completely, utterly, wonderfully useless. It wasn't a cure for cancer, a climate model, or a financial forecast. It was a highly specific, abstract mathematical puzzle with no immediate practical application. So why, then, did this seemingly pointless achievement make global headlines? Why did scientists, engineers, and governments around the world sit up and take notice? The answer wasn't in what they solved, it was in how they solved it. They didn't use a classical supercomputer like Summit. They used a different kind of machine entirely, a quantum computer. This complex, often bizarre-looking device, using superconducting, circuits cooled to temperatures colder than deep space, was able to manipulate information in a way classical computers simply cannot. It harnessed the strange, counterintuitive rules of the quantum world, the world of the very, very small, and used them to perform a calculation that was functionally impossible for its classical counterpart. This moment, this demonstration of quantum advantage was a landmark, not because of the specific answer it produced, but because it proved definitively that quantum computers are not just theoretical curiosities. They are real, and they have the potential to solve problems that were once thought unsolvable. But to understand how we got here, to appreciate the decades of struggle, frustration, and brilliant insight that led to that 3-minute calculation, we need to step back, way back, over 40 years in fact, to a quiet mansion in Massachusetts in 1981. November 1981. The world of computing is rapidly evolving, but still feels grounded in the familiar rules of physics we see all around us. Bits are either 0 or 1, like a light switch being either on or off. Calculations are step by step, like following a recipe. Yet, at the MIT Endicott Mansion, something different was happening. It was called the First Conference on the Physics of Computation. This wasn't your typical computer science conference. It was a meeting of minds from diverse fields, physicists, mathematicians, computer scientists, all grappling with the fundamental nature of computation. Luminaries like Freeman Dyson, known for his work in quantum field theory, John Wheeler, who coined the term black hole, Ed Fredkin, and Charlie Bennett, pioneers in reversible computing. They gathered not just to share results, but to dream, to discuss the very limits of what computation could be. And among them was a figure who, at first glance, might seem like an unlikely candidate to spark a revolution in computing: Richard Feynman. Now, Richard Feynman wasn't known for building computers. He was, at this point, a titan of theoretical physics, a Nobel laureate celebrated for his groundbreaking work in quantum electrodynamics, describing how light and matter interact at the quantum level. He'd worked on the Manhattan Project, helped crack the challenge of transporting liquid helium, and was legendary for his brilliant mind and unconventional approach to everything. He was an educator who could explain complex ideas with astonishing clarity, famous for his Feynman lectures on physics and his insatiable curiosity about the world. But a computer scientist? Not really. Yet, Feynman had a gift that transcended disciplines, the ability to ask the deepest, most fundamental questions. He wasn't afraid to look at a problem from a completely different angle, often arriving at insights that others missed. During his talk at that 1981 conference titled Simulating Physics with Computers, Feynman delivered a line that, in retrospect, effectively willed the field of quantum computing into existence on the spot. He said, with characteristic Feynman bluntness, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem, because it doesn't look so easy." Let's unpack that famous line. To the physicists in the room, the statement, "Nature isn't classical," was almost a truism. Quantum mechanics, the bizarre rules governing the subatomic world, had been around for over half a century. Thanks to pioneers like Niels Bohr, Albert Einstein, Erwin Schrödinger, and Werner Heisenberg, they knew that particles don't behave like tiny billiard balls. They can exist in multiple places at once, influence each other instantaneously across vast distances, and seem to defy common sense. Early quantum mechanics was indeed a patchwork of puzzling observations. Think of the famous double-slit experiment, where particles like electrons seem to act like waves, creating interference patterns even when sent one by one. Or the photoelectric effect, where light, usually thought of as a wave, behaves like particles, photons, when knocking electrons off a metal surface. The ultraviolet catastrophe, a problem in understanding heat radiation, also hinted that classical physics was missing something fundamental at small scales. It was the work of scientists, like Schrödinger, that began to unify these strange observations into a solid, mathematically rigorous theory. Schrödinger's master equation, often called the Schrödinger equation, became the central pillar. He built his theory partly on a concept familiar from classical physics: energy conservation. Just as a ball rolling down a hill exchanges potential energy for kinetic energy, he reasoned that particles at the quantum scale would follow similar energy rules. But as he applied his equation, the strangeness of quantum mechanics became mathematically apparent. Take the simplest problem he could imagine: a particle, like an electron, trapped inside a tiny box with impenetrable walls. If you draw the potential energy for this setup, it looks like a well: zero energy inside, infinite energy outside. Solving. The Schrödinger equation for this scenario doesn't give you just one answer for the particle's state and energy. It reveals a whole family of possible states, each with a unique, discrete energy level, like steps on a ladder, or specific notes on a musical scale. These are the eigenstates. And here's where it gets really quantum. The math showed that you could combine these unique solutions. If you take the first state, the lowest energy, most stable one, let's call it 0, and the second state, the next energy level up, let's call it 1, you can add them together with different weights or coefficients. The resulting state is a superposition, a combination of the 0 state and the 1 state existing simultaneously. The particle is, in a very real quantum sense, a little bit in state 0 and a little bit in state 1 at the same time. It's not like flipping a classical coin that's either heads or tails. It's like the coin is spinning, simultaneously heads and tails, until you stop it and look. This very same physics, the existence of discrete energy levels and the possibility of superposition, governs the behavior of atoms and molecules. This is why Feynman, with his deep understanding of physics, believed that if you wanted to simulate nature accurately, especially complex quantum systems like molecules interacting or materials behaving strangely at low temperatures, a classical computer fundamentally built on zeros and ones wouldn't cut it. You needed a computer that could inherently represent and manipulate these quantum superposition states. You needed a quantum computer. Feynman's vision was profound. He saw that classical computers, no matter how fast, were like trying to simulate a fluid by tracking every single water molecule individually. Quantum mechanics offered a different way, one that inherently captured the collective, wave-like behavior that was missing in classical simulations. Feynman's talk was inspiring, a powerful intellectual seed planted in fertile ground. But for several years, that seed remained dormant. In principle, the idea of a computer based on quantum principles was sound. Early theoretical work in the 1980s explored the concept, but it didn't immediately yield anything that screamed revolution. A couple of algorithms for secure communication were proposed, but they didn't deliver the kind of exponential speed-up for simulating nature that Feynman had envisioned. Progress was slow. It felt like a fascinating theoretical side alley rather than the future of computing. The quantum computing community was searching for its killer app, a problem where a quantum computer could provide a clear, undeniable advantage over its classical counterpart. They needed a proof of concept that went beyond abstract theory. Then, in the early 1990s, things began to shift. A turning point arrived in 1992 with two theoretical physicists, David Deutsch and Richard Feynman. They developed an algorithm for a quantum computer that achieved a true speed-up. The problem they tackled was abstract, but crucial for demonstrating potential. Imagine you have a mathematical function hidden away, and you're allowed to feed it inputs and see the output. You know the function has only two possible natures. It's constant. No matter what input you give it, the output is always the same, either always 0 or always 1, 2. It's balanced. For half of the possible inputs, the output is 0, and for the other half, the output is 1. Your task: figure out if the function is constant or balanced. A classical computer, in the worst case, would have to check slightly more than half of all possible inputs to be absolutely certain. As the number of possible inputs grows, the time required for a classical computer increases. Deutsch and Feynman showed that a quantum computer could solve this problem in a single shot. One quantum operation was enough to determine whether the function was constant or balanced, regardless of how many inputs were possible. This was it. The first example of a problem where a quantum algorithm offered a demonstrable, superclassical advantage. It was a vital step, showing that quantum speedup wasn't just a theoretical fantasy. While the Deutsch-Feynman algorithm was incredibly important to theorists, the next breakthrough was one that captured the world's attention and truly launched the global race to build quantum computers. This brings us to the mid-1990s and a mathematician working at Bell Labs, a hotbed of scientific innovation named Peter Shor. Shor was one of the scientists asked to review a paper by a colleague, Daniel Simon, for acceptance to a major computing conference, the Symposium on the Theory of Computing, ACE2C94. Simon's paper described an efficient quantum algorithm for solving a problem that, like Deutsch-Feynman's, seemed incredibly abstract and, frankly, rather useless on the surface. The problem went something like this. You have a hidden function, feux. This function has a secret pattern, determined by a hidden secret string, let's call it S, a binary number. The pattern is that for any two inputs, x and y, the function gives the same output, fx, adders fy, if and only if x and y differ by. That secret strings, or more precisely, x XOR S chapotfurs, using binary addition without carry. Your goal? Find the secret string S. Seems utterly academic, almost frivolous, right? This perception likely contributed to the conference committee's decision to reject Simon's paper, despite Shor voicing his disagreement. But Peter Shor, with his deep mathematical insight, saw something in Simon's seemingly useless problem. PTE, realized that Simon's algorithm was, at its core, a highly efficient way for a quantum computer to find the period of a function. If a function repeats itself, Simon's algorithm could quickly find how often it repeats. Separately, around the same time, other mathematicians had been developing new techniques in number theory, demonstrating how many difficult problems in that field could be transformed into period-finding problems. Shor, connecting these two disparate threads, Simon's quantum period-finding algorithm and the number theorists' realization about transforming problems, had a stroke of genius. He realized that one of the most famous and difficult problems in number theory that could be reduced to period finding was the problem of factoring large numbers. Factoring means breaking down a number into its prime factors. For example, finding that 15 is 3 times 5, or that 12 is 2 times 2 times 3. For small numbers, this is trivial. But for very large numbers, numbers with hundreds or even thousands of digits, factoring becomes computationally incredibly hard. So hard, in fact, that the security of nearly all modern encryption systems, the locks that protect our online banking, our emails, our national secrets, is based on the assumption that factoring large numbers is practically impossible for classical computers within a reasonable time frame. Shor's algorithm, published in 1994, provided a method for a quantum computer to factor large numbers exponentially faster than any known classical algorithm. This wasn't a useless problem anymore. This was the killer application the field had been waiting for. Imagine cracking the code behind secure communications. Imagine unlocking financial transactions. Imagine compromising national security secrets protected by the strongest classical encryption. Shor's algorithm brought quantum computing out of the academic basement and onto the global stage, giving it immense and sometimes unsettling real-world implications in cybersecurity, finance, and national defense. The reaction was immediate and intense. Conferences were quickly convened. Governments took notice. Peter Shor himself was reportedly questioned by the NSA, the U.S. National Security Agency, the very organization most concerned with cryptography and code breaking. The Iowa message was clear. Quantum computing was no longer just a theoretical playground. It was a potential paradigm shift with serious consequences. And with that shift, the pressure mounted. The theorists had done their part, demonstrating the potential power of quantum computers. Now, it was the experimentalists' turn. It was time to get to work building these machines. Building a quantum computer, however, is not like building a regular computer. It's not just miniaturizing transistors. You're trying to control quantum states, incredibly fragile, ephemeral things that exist in a superposition of possibilities until you disturb them, before they could even start soldering wires, or whatever the quantum equivalent would be. The experimentalists needed a roadmap, a set of requirements, a blueprint for what a functional quantum computer would need to be able to do. This blueprint was laid out by David DiVincenzo, a theoretical physicist in the late 1990s. He outlined what became known as the DiVincenzo criteria, a widely accepted checklist for any physical system aspiring to be a quantum computer. Think of them as the essential building blocks, the non-negotiables. He listed 5 key criteria for the quantum computer itself, and 2 more if you wanted to connect them into some kind of quantum internet, a concept that feels even more futuristic. Since we're focusing on the computer itself today, let's look at the first 5. A scalable physical system with well-characterized qubits. You need the basic building block of quantum information, the qubit, and you need to be able to make many of them and understand their behavior precisely. The ability to initialize the state of the qubits into a simple state. You need to be able to set your quantum computer to a known starting point before you run a calculation. Long relevant quantum coherence times, The fragile quantum states need to last long enough to perform operations on them before they lose their quantum properties due to noise. A universal set of quantum gates. You need a set of operations, like logic gates in a classical computer, that allow you to manipulate the qubit states and perform any possible quantum computation. A qubit-specific measurement capacity. At the end of the calculation, you need to be able to read out the final state of each qubit to get your answer. These criteria gave experimentalists their marching orders. Whatever system they chose, be it trapped atoms, superconducting circuits, photons, or something else, it had to satisfy this demanding list. Let's take a moment to understand the star of the show here, the qubit. Remember how a classical computer uses bits, which are like light switches, either strictly off, 0, or strictly on, quaternice. 1. The quantum analog is the qubit, or quantum bit. Physically, a qubit isn't one specific thing. It can be an electron's spin, the energy state of an atom. The direction a photon is polarized, or, as we'll see, the state of a tiny electrical circuit. But in every case, the underlying physics is similar. When you look at the quantum mechanics of these systems, you find those ladders of energy levels we saw with Schrödinger's particle in a box. To create a qubit, you simply choose two of these levels, usually the lowest energy one as your A0 state, and the next one up as your 1 state, and restrict your operations to just these two. So far, sounds a bit like a fancy classical bit, right? Just 0 or 1. But quantum mechanics gives us two incredibly powerful additional tools. First, superposition. Unlike that classical light switch, or the spinning coin that must land heads or tails, a qubit, thanks to quantum mechanics, can exist as a combination of both the 0 and 1 states simultaneously. It's not one or the other, it's both, in varying proportions. Imagine mixing paint. You can have pure blue, danso, pure yellow, to 1, or a shade of green that's 50% blue and 50% yellow, or 70% blue and 30% yellow, and so on. A qubit can be in any arbitrary combination of its 0 and 1 states. This allows a single qubit to, in a sense, represent both possibilities at once. However, and this is crucial, as soon as you measure the qubit, try to see if it's 0 or 1. Its superposition collapses. It's forced to choose probabilistically. The probability of collapsing to 0 or 1 depends entirely on the weights of the combination it was in before measurement. If your superposition was 90% 0 and 10% 1, about 90% of the time you measure, you'll get 0, and 10% of the time you'll get 1. Measuring inherently changes the state. Second, entanglement. This is where things get truly weird and powerful. Entanglement is a special, deeply linked form of superposition involving two or more qubits. Normally, two qubits are independent. Changing one doesn't affect the other. But through interaction, they can become entangled. Imagine two coins that, once entangled, somehow become linked. If you measure one coin and find its heads, you instantly know the other coin must be tails, or heads, depending on the specific entangled state. Even if they are miles apart, measuring one instantaneously influences the state of the other. Einstein famously called this spooky action at a distance, and it's one of the most counterintuitive aspects of quantum mechanics. In quantum computing, entanglement is often called the workhorse. See, it allows the states of multiple qubits to be correlated in ways impossible classically. By creating specific entangled states and performing operations on them, quantum algorithms can explore many possibilities simultaneously, and through quantum interference, a bit like waves canceling or reinforcing each other, amplify the probability of measuring the correct answer while suppressing the probabilities of wrong answers. This funneling of probability towards the solution is a key source of quantum speedup. So, those are the core concepts. Qubits that can be in superposition and entanglement that links them together. DiVincenzo's criteria essentially say, you need lots of these qubits. Scalable system. You need to put them where you want them to start. Initialize. You need them to stay quantum long enough to do stuff. Coherence. You need tools to manipulate and entangle them. Gates. And you need to be able to see what they are at the end. Measurement. Armed with Shor's motivation and DiVincenzo's blueprint, experimental physicists around the world rolled up their sleeves and began the monumental task of actually building these machines. The first step wasn't trying to build a machine to factor numbers. It was much simpler, much more fundamental. Build a single, isolated qubit that satisfied the basic criteria. One of the key figures who took up this challenge was David Wineland, a physicist at NIST, National Institute of Standards and Technology. Wineland wasn't a newcomer to controlling microscopic systems. He had spent much of his career perfecting techniques for trapping and manipulating individual atoms using electromagnetic fields and slowing them down to near absolute zero temperatures using lasers, a process called laser cooling. His lab was renowned for its precision and control over individual particles, work that was initially aimed at creating incredibly accurate atomic clocks and sensors, not necessarily quantum computers. Wineland's journey into quantum computing wasn't a straight line. It was an evolution driven by curiosity and the recognition of potential. He was already a master of controlling single particles, the perfect scale for quantum mechanics. As the whispers of quantum information theory grew louder in the physics community in the 1990s, Wineland saw that his unique toolkit, trapped ions and lasers, might be exactly what was needed. The spark came in 1995 when he read a paper by Peter Shor and Ignacio Cirac. This theoretical paper proposed a specific, step-by-step recipe for using trapped ions to perform quantum logic gates, the operations needed to build a quantum computer. Suddenly, Wineland saw how the tools he had spent decades refining could be applied directly to build the components described in DiVincenzo's criteria. His fundamental physics experiments had unexpectedly prepared him for the cutting edge of computation. The path was still incredibly challenging. Quantum computing requires unprecedented levels of isolation and control. Battling decoherence, the loss of quantum properties due to interaction with the environment, was a constant fight. Forcing ions, which naturally repel each other, to interact in a controlled quantum way while keeping them isolated from noise was a daunting technical hurdle. Wineland's team's breakthrough came with their choice of ion and their ingenious measurement technique. They decided to use a beryllium ion. The different energy levels within this ion could serve as the 0 and 1 states of their qubit. Lasers could be precisely tuned to manipulate the ion's state, putting it into superposition or performing gates. But the most elegant part was the measurement. Remember, you need to read out the qubit's final state. How do you tell if a single microscopic ion is in the 0 or 1 state without disturbing it too much before you're ready? Wineland's team used a clever trick based on fluorescence. They shone a carefully tuned laser on the ion. If the ion was in the 1 state, the laser would excite it, and it would fluoresce, emitting photons that could be detected by a camera. If it was in the 0 state, the laser wouldn't interact with it in the same way, and the ion would remain dark. This simple, beautiful solution allowed them to reliably see the state of their single qubit. It was one of the first demonstrations of a single qubit being initialized, manipulated, and measured in a laboratory setting. When Wineland's team succeeded in building and controlling this first trapped ion qubit in 1995, The response from the scientific community was electrifying. Theorists who had been working on abstract ideas for years finally had proof that these concepts could be realized in the physical world. It showed that quantum information wasn't just ink on a page. It was something that could be stored, manipulated, and read out in a lab. While there were still countless experimental challenges ahead to scale this up, it was the critical proof of concept needed to ignite an experimental revolution in quantum computing hardware across various physical systems. Wineland's pioneering work, alongside that of Serge Haroche in France, who achieved similar control over photons in a cavity, earned them the Nobel Prize in Physics in 2012. Their fundamental demonstrations of controlling individual quantum systems laid the groundwork for all quantum computing hardware that followed, including the trapped ion systems used by companies like IonQ and Quantinuum today. With Wineland's success and the motivation provided by Shor's algorithm, research groups worldwide intensified their efforts, exploring many different ways to build qubits and quantum computers. They experimented with nuclear magnetic resonance, like the technology behind MRI scanners, using the spin of atomic nuclei, with electron spins trapped in semiconductors, with neutral atoms manipulated by lasers, similar in spirit to trapped ions but using uncharged particles, with photons using particles of light as carriers of quantum information, and with superconducting circuits. While many of these platforms have seen exciting progress and have startup companies pushing their development, one technology has emerged as a clear frontrunner in terms of current scale and demonstration of quantum advantage: superconducting circuits. When you see pictures of Google's or IBM's quantum computers, those beautiful chandelier-like structures cooled to near absolute zero, you're usually looking at superconducting qubits. These qubits are based on tiny electrical circuits, made from special materials that, when cooled to extremely low temperatures, allow electric current to flow without resistance. They become superconductors. Researchers in the early 1990s had already shown that these circuits at low temperatures could exhibit quantum mechanical behavior. They could behave like artificial atoms with discrete energy levels that could potentially serve as qubit states. The modern era of superconducting qubits really began in 1999 with Yasunobu Nakamura's paper demonstrating the first charge qubit, the Cooper pair box. This device used a tiny superconducting island connected to a larger superconducting reservoir by a special quantum mechanical switch called a Josephson junction. By carefully controlling a voltage applied to the island, they could control the number of Cooper pairs of electrons bound together in superconductors on the island. The difference between having n Cooper pairs or n+1 Cooper pairs on the island defined the 0 and 1 states of this new type of qubit. It was a groundbreaking demonstration, but controlling the Cooper pair box was difficult. It was incredibly sensitive to tiny fluctuations in electrical charge in the environment, leading to very short coherence times. The quantum states would decay in mere nanoseconds, far too quickly to perform meaningful computations. This was like trying to have a complex conversation with someone who instantly forgets everything after a fraction of a second. In the early 2000s, a team at Yale University set out to overcome these limitations. They introduced a new theoretical framework called Circuit Quantum Electrodynamics, or CQED. This wasn't a new theory from scratch. It adapted concepts from cavity QED, which describes how atoms interact with light trapped in a box-like cavity, to the world of superconducting circuits and microwave photons. In CQED, the superconducting qubits are treated like artificial atoms, and tiny superconducting resonators, like miniature antennas, act like the cavities, allowing precise control and measurement of the qubits using microwave pulses. This framework provided the mathematical language and experimental techniques needed to gain much better control over superconducting qubits. One of the most important contributions from the Yale group was the invention of the transmon qubit. The transmon was a brilliant refinement of the Cooper pair box design. By changing the junction properties, they made the qubit much less sensitive to charge noise, the main culprit behind the short coherence times of earlier designs. They effectively sacrificed a bit of tunability, the ability to easily change the qubit's frequency for much greater stability. This was a crucial trade-off. It was like building a sturdy, reliable switch instead of a super flexible but easily broken one. This invention made the transmon a practical and scalable design, and it's now the workhorse qubit used by major players like IBM and Google in their quantum computing efforts. Over the past 2 decades, continuous engineering improvements in transmon design, fabrication, and control have pushed coherence times from nanoseconds in early charge qubits to tens of microseconds, and now approaching milliseconds in the best devices. A 1,000-fold improvement. While still short by classical standards, milliseconds is still very fast. It's long enough to perform hundreds or even thousands of quantum operations, and it brings the prospect of quantum error correction, techniques to protect fragile quantum information into closer view. And that, finally, brings us back to where we started. The Google team in 2019. It was using a system built with these high-coherence transmon qubits, a processor they called Sycamore, that Google was able to perform that now-famous calculation. The specific algorithm they ran wasn't Shor's algorithm or a simulation of a useful molecule. It was a carefully designed problem specifically intended to be extremely difficult for a classical computer, but relatively straightforward for their quantum processor. The problem was essentially to verify that the quantum circuit was behaving randomly as expected, a task useful for benchmarking the quantum computer itself, but not for solving any real-world challenge. The point wasn't the solution's utility. The point was the demonstration. It showed that they had engineered a system with enough qubits, 53 in this case, with sufficient coherence times, enough control, gates, and reliable measurement to tackle a problem that was provably beyond the reach of the world's best classical supercomputers in any reasonable time frame. They had achieved quantum advantage. This paper wasn't a headline because the problem was important. It was a headline because it proved that the dream born in 1981, nurtured by theoretical breakthroughs in the 90s, and painstakingly built peace by peace in labs around the world, was finally reaching a critical inflection point. It showed that while universally useful quantum computers capable of breaking encryption or simulating complex drug interactions might still be years away, we can engineer and control quantum systems to a degree previously thought impossible. Painstaking was a loud, clear signal to the world. The quantum era is coming, and the progress is accelerating. So, what can we take away from this incredible journey? From a physicist pondering the nature of simulation in 1981 through abstract mathematical puzzles, to the painstaking engineering of microscopic quantum machines, culminating in solving a useless problem faster than any classical computer could? Perhaps. It's a lesson in the power of fundamental curiosity. Feynman wasn't trying to build a better supercomputer. He was asking how to truly simulate nature. Simon wasn't trying to break encryption. He was exploring the power of quantum algorithms for obscure mathematical problems. Their work, born of deep curiosity, became the unexpected foundation for a technological revolution. It's also a lesson in persistence and the slow, often frustrating march of progress. From nanosecond coherence times to milliseconds, 1,000-fold. Improvement is massive in science, but it takes years, even decades, of dedicated work, battling noise, refining techniques, and facing countless failures. Building these machines is one of the hardest engineering challenges humanity has ever undertaken. And maybe Most importantly, it's a lesson in seeing potential where others see only uselessness. If Peter Shor hadn't looked at Simon's useless, period-finding problem and connected it to the very real-world problem of factoring large numbers, the quantum computing revolution might have remained a theoretical curiosity for much longer. Sometimes, the most groundbreaking ideas emerge when you combine seemingly unrelated concepts, when you dare to ask, what if this abstract thing could be applied over here? So, next time you encounter something that seems purely academic, abstract, or even completely useless, pause for a moment. Ask yourself, what are the fundamental principles at play? Could this idea, in combination with something else, unlock a new way of thinking or doing things? Could this useless puzzle be the key to a problem I haven't even considered yet? Curiosity, persistence, and the ability to find unexpected connections. These are powerful tools, not just in the lab, but in navigating our own lives and challenges. The quantum journey reminds us that big revolutions often start with small, seemingly insignificant questions pursued with unwavering dedication. The quantum future is still unfolding. What problems will these machines eventually solve? How will they change our lives? We're only just beginning to find out. It's a wild, exciting, and sometimes spooky journey ahead. Thank you for joining us on this exploration of the quantum leap. If this story sparked your own curiosity about the universe and technology, please consider hitting that subscribe button and joining our community. We'll keep exploring the fascinating frontiers of science and innovation together.